Hello, so in this video we're going to look at section 1.1, functions and function notation. There will be four main topics that we're going to look at. Along with that, in the description below, there will be the video chapters, so you can jump to the various sections that you would like to see. There'll be a link to the Openstax textbook, the first and second edition. There'll be a shared folder with additional notes and resources that you're welcome to check out, and a survey at the bottom. So first, we're going to start with determining whether a relation is a function. And so let's start talking about what a relation is and what a function is. So we can see that a relation is like an ordered pair set. And within the ordered pair set, we have the first component, which will be your domain or your x values. And we have a second component in the ordered pair that is your y values, which is the range. So if we were to look at this example and we wanted to list out our domain and range, for the domain being our x values, we would have 1, 2, 3, 4, 5, and 6 within those ordered pairs. And then for our range, we would have 20, 21, 22, 23, 24, and 25. So since we know that a relation is initially an ordered pair set, we can look at what a function is, and a function is just a relation in which each possible input value leads to exactly one output value. And then for it to be a function is a function if the relation to x and y, if the x corresponds to only one y. So for example, we could look at three different cases. So in the first case, we could look at 3x and 3y points, and we can see that we would have one x corresponding with one y, and so it would be a function. We have another case where we could have 3x values and 2y values, and we would have one y value to 2 x's and one y, and one x with one y, and we can see that it's still a function because it also fits our definition. But then we could have another situation where we have 2 x values and 3 y values, and we can see that one x value corresponds with 2 y values and one x value corresponds with one y value, and we can see that that is not a function. So next we want to look at a function notation, and you've probably seen it before. So before, you would see y equals x plus 5. And now, since we're going to start seeing function notation, you're going to start seeing transformations for various graphs. You're going to now see f of x, g of x, or h of x equals x plus 5. And this x plus 5, this f of x is still the same thing as y, so they can go hand in hand with each other. So f of x is equal to y. So next, we're going to look at finding the input-outputs of a function. So we're going to look at function notation for f of x, given some value, and we're going to plug in, let's say, 5 for x, and so we would put in a 5 for everywhere we would see an x, and we would just solve and get a value, or an equation. So first, we're given f of x is equal to 2x minus 5, and we want to evaluate for a, b, c, d, e, and so on. And so we're going to start with a. So since we know that f of x is 2x minus 5, and since we want f of negative 3, you would plug in a negative 3 everywhere we see an x, so 2 times negative 3 minus 5. If we plug that into our calculator, we would see, and we would get f of negative 3 is equal to negative 11. And if you wish to write this as an ordered pair, you could write it as negative 3, negative 11. Next, we want to look at f of 2. So we would have our equation that we're given, f of x is equal to 2x minus 5. And everywhere we see an x, we're going to plug in a 2. So f of 2 equaling 2 times 2 minus 5. And we would get f of 2 would equal negative 1. If we were to write this as an ordered pair, we would have 2, -1. And for C, we have f of -a. So anywhere we see an x, we're going to plug in a -a. And so we would just get a -2a minus 5 as our answer, and that would be it. Then we're given E, f of a plus h. So we can plug that anywhere we see an x, we're going to plug in an a plus h. So if we had an a plus h, so f of a plus h, we're going to plug in an a plus h wherever we have an x. So 2 in parentheses a plus h minus 5. We would take our 2 and distribute it into both of them. And so our answer would, for f of a plus h, would be 2a plus 2h minus 5. So next we're given that f of x is equal to x squared minus 3x plus 1. And we want to evaluate for a, b, c, d, and e. So if we wanted to evaluate for a, we can see that a is equal to f of -3. And so everywhere we see an x, we would plug in a -3. If we plugged into our calculator, we would see that we would get f of -3 would equal 19. If we were to write that as an ordered pair, we would get -3, 19. For b, we're asking for f of 2. So anywhere we see an x, we would plug in a 2. If we plugged into our calculator, we would get that f of 2 would equal -1. And if we were to write that as an ordered pair, we would have 2, -1. If we look at C, we want f of -a, so anywhere we see an x, we're going to plug in a -a. So we would get -a in parentheses squared minus 3 -a plus 1. And if we rewrite this, we would get f of -a is equal to a squared minus plus 3a plus 1. And that would be our answer. For D, we want negative f of a. So we can look at plugging in a wherever we see an x. So we would get a squared minus 3a plus 1. And then we would include our negative. And we would take our negative and distribute it out into everything. And so we would get negative f of a is equal to negative a squared plus 3a minus 1. So next we're given E is equal to f of a plus h. And so anywhere we see an x, we would plug in an a plus h. So we would get in parentheses a plus h squared minus 3 in parentheses a plus h plus 1. If we were to FOIL a plus h in parentheses squared and we were to distribute 3a plus h in combined like terms, we would get that f of a plus h would equal a squared plus 2ah plus h squared minus 3a minus 3h plus 1. So next we want to determine whether a equation is a function. So the idea with these is we want to find where we don't want it to be undefined. So if we were given a rational expression with an x or y or variable in the denominator, we would try to figure out where it would not equal 0 because that would give it undefined. We could plot our points on an x, y t-chart and see whether we're a function. So making sure that only x corresponds with only one y. So first we're given x equals y minus 1. And if we were to find the value for y, we could add 1 to both sides and we would get y is equal to x plus 1. And if we were to look at the graph, we would see that it would be linear. And so it would be a function. So next we're given y equals -2x squared plus 40x. And if we looked at factoring this or flipping it to make sure, see if it's a function, we could flip our signs. So we would have x equals -2y squared plus 40y. If we were to factor, we could pull out a negative 2y, and we'd be left with a y plus 20. If we were to set them both equal to x, we would have x is equal to negative 2y, and x is equal to y plus 20. And we can also see that this is a quadratic, so we would have a function. So next we're given x equals y squared, and if we were to solve for y, we could take the square root, and we would have plus or minus square root of x is equal to y, and that would just be cubed. But it would not be a function, because if we were to look at the graph, or look at a t-chart, we would see that if we plug in a 4, we're going to see that we're going to get 2y. So we're going to get a negative 2 and a positive 2. So we have two x's, and so it's not going to be a function. So next, we're going to determine whether a function is one-to-one. And so we can use various ways to see if it's a function, and then if it's a function, then we can see if it's one-to-one. So we can see that a one-to-one function is in which each output corresponds to exactly one input. We can see that we can use the vertical line test to see if the graph represents a function, and if it represents a function, then we can use the horizontal line test to see if it is one-to-one. So for example, if we were given this graph, we can see on some points where the vertical line test would pass. So if we looked at the points here and the points over here, we would see that the points do pass. But since we hit 2 points right here, we would not pass our vertical line test, nor would we pass our horizontal line test. So it is not a function, and it is not one-to-one. So next we could look at another graph, and so if we had something like this, we would see that on the vertical line test, we would pass it because we could see some points where it would hit, and it would still represent a function. And then if we were to look at our horizontal line test, it would pass because it would only hit 1 point the whole time. And so for this graph, it would be one-to-one, and it would be a function.